NENOMATICA, where mathematics meets YouTube excellence. Welcome to our math lesson on standard form polynomials. A polynomial is said to be in standard form when it's arranged in descending powers of the variable. The general form of a polynomial in the variable x is represented as p of x equals a sub n times x to the power of n plus a sub n minus 1 times x to the power of n minus 1 plus a sub n minus 2 times x to the power of n minus 2 plus a sub 1 times x plus a sub 0. Here, the values a sub n minus 1, and so on are called coefficients, and n is the degree of the polynomial. Let's look at an example. Consider this polynomial p of x equals x squared minus 7x to the 4th power plus x to the 5th power minus 3x plus 2 plus x cubed. This polynomial is not in standard form because the terms are not arranged in descending powers of x. To convert this polynomial into standard form, we need to rearrange the terms in descending powers of x. So, we will start with the term with the highest power, which is x to the 5th power, followed by x to the 4th, x cubed, x squared, x to the 1st power, and finally the constant term. Now, our polynomial is in standard form. P of x equals x to the 5th power minus 7x to the 4th power plus x cubed plus x squared minus 3x plus 2. The powers of x are now in descending order. 5, 4, 3, 2, 1, and 0. This makes the polynomial easier to analyze and work with. From this standard form, we can easily identify important properties of the polynomial. The degree of this polynomial is 5, which is the highest power of x. The leading coefficient is 1, which is the coefficient of x to the 5th power. Let's identify all the coefficients in our standard form polynomial. The coefficient of x to the 5th power is 1. The coefficient of x to the 4th power is negative 7. The coefficient of x cubed is 1. The coefficient of x squared is 1. The coefficient of x is negative 3. And the constant term, or coefficient of x to the power of 0, is 2. The standard form of a polynomial is important for several reasons. First, it makes it easier to identify the degree and leading coefficient. Second, it provides a consistent way to express polynomials, which is essential when comparing or working with multiple polynomials. Third, many algebraic operations and theorems assume polynomials are written in standard form. Now, let's try a practice problem. Convert this polynomial to standard form. Q of x equals 3 minus 2x squared plus 4x plus 7x cubed. Take a moment to work on this problem. Pause the video if you need more time. The solution is Q of x equals 7x cubed minus 2x squared plus 4x plus 3. Let's verify. We've arranged the terms in descending powers of x, starting with x cubed, then x squared, then x to the 1st power, and finally the constant term. To summarize what we've learned today, a polynomial is in standard form when its terms are arranged in descending powers of the variable. This form makes it easier to identify the degree and coefficients of the polynomial. Remember, to convert a polynomial to standard form, simply rearrange the terms so that the powers of the variable decrease from left to right. Welcome to our video on polynomials that are identically 0. We'll explore what it means for a polynomial to be identically 0 and the necessary and sufficient condition for this property. Let's start with the definition. A polynomial is said to be identically 0 if it equals 0 for all possible values in its domain. For a polynomial to be identically 0, it is necessary and sufficient that all of its coefficients are 0. Let's consider the general form of a polynomial. We can write a polynomial of degree n as p of x equals a sub n times x to the power of n, plus a sub n minus 1 times x to the power of n minus 1, plus a sub 2 times x squared, plus a sub 1 times x, plus a sub 0. Now, let's prove our theorem. First, if all coefficients of the polynomial are 0, that is, if a sub n equals a sub n minus 1 equals a sub 2 equals a sub 1 equals a sub 0 equals 0, then the polynomial p of x equals 0 for any value of x. Now for the second part, we'll show that if a polynomial is identically 0, then all of its coefficients must be 0. So, if p of x equals 0 for all x, then p of x equals 0 for x equals 0 as well. This gives us a sub 0 equals 0. Now, let's rewrite our polynomial equation. Since a sub 0 equals 0, we can rewrite our original polynomial as a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus a sub 2 times x squared plus a sub 1 times x equals 0. Factoring out x from all terms, we get x times the quantity a sub n times x to the power of n minus 1 plus a sub 2 times x plus a sub 1 equals 0. Now, using the zero product property, if the product of two expressions is 0, then at least one of the factors must be 0. Since x can take any value except 0, because we've already used x equals 0 earlier, the second factor must equal 0 for all non-zero values of x. That is, a sub n times x to the n minus 1 plus a sub 2 times x plus a sub 1 equals 0 for all non-zero x. But since a polynomial that equals 0 for all non-zero values must also equal 0 for all values by the principle of polynomial continuity, we now have a new polynomial of degree n minus 1 that is identically 0. By repeating our earlier argument with this new polynomial, we find that a sub 1 must also equal 0. Continuing this process, we can conclude that all coefficients a sub n minus 1, a sub 2, a sub 1, and a sub 0 must be 0. Therefore, we have proven that for a polynomial to be identically 0, it is necessary and sufficient that all of its coefficients are 0. This is an important theorem in polynomial algebra that helps us understand when two polynomials are equal and forms the basis for many other results in algebraic theory. Today, we'll explore the concept of identical polynomials and how to determine when two polynomials are equal. First, let's understand the basic principle. Two polynomials are identical if they have the same value for all values of the variable. This means their coefficients for corresponding terms must be equal. For two polynomials to be identical, all corresponding coefficients must be equal. Let's represent two general polynomials p of x and q of x of degree n. If these polynomials are identical, their coefficients must match term by term. For this equation to be identically 0, each coefficient must be 0. This gives us a system of equations where each a sub n equals b sub n, a sub n minus 1 equals b sub n minus 1, and so on down to a sub 0 equals b sub 0. Now, let's look at our first example. We want to determine values of a, b, and c that make these two polynomials identical. To solve this problem, we need to set these polynomials equal to each other. Let's write p of x is identical to q of x and expand the equation. Now, we need to compare the coefficients of each power of x. For the coefficient of x cubed, we have a minus 1 equals 2, which means a equals 3. For the coefficient of x squared, we have negative 3 equals negative 3, which is already satisfied. For the coefficient of x to the first power, we have a plus b plus 2 equals negative 1. For the constant term, we have c minus 2 equals b minus 1. Let's solve this system of equations to find the values of a, b, and c. We already know that a equals 3. Substituting this into the equation for the coefficient of x, we get 3 plus b plus 2 equals negative 1, which simplifies to b equals negative 6. Finally, for the constant term, we have c minus 2 equals b minus 1. Substituting b equals negative 6, we get c minus 2 equals negative 6 minus 1, which is negative 7. Solving for c, we get c equals negative 5. Therefore, the solution to our first example is a equals 3, b equals negative 6, and c equals negative 5. These values make the two polynomials identical. Let's move on to a second example. In this case, we have a factored polynomial p of x equal to quantity x squared minus 1 times quantity x plus 2. And we want to find values of a, b, and c that make it identical to polynomial q of x, which equals x cubed plus ax squared plus bx plus c. First, we need to expand the factored form of p of x to compare it with q of x. We'll multiply quantity x squared minus 1 by quantity x plus 2. This gives us x cubed plus 2x squared minus x minus 2. Now, we can set the expanded form of p of x equal to q of x. We have x cubed plus 2x squared minus x minus 2 equals x cubed plus ax squared plus bx plus c. Comparing the coefficients of x cubed, both sides have a coefficient of 1, so that's already satisfied. For the coefficient of x squared, we have 2 equals a, so a equals 2. For the coefficient of x, we have negative 1 equals b, so b equals negative 1. For the constant term, We have -2 equals c, so c equals -2. Therefore, the solution to our second example is it equals 2, b equals -1, and c equals -2. With these values, the two polynomials will be identical. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.